What we have next is a handful of examples. The first example here says that a study of 150 randomly selected occupants in passenger cars and then 200 other randomly selected occupants in pickup trucks showed that apparently 86% of the passengers in the car and 74% of the people inside the pickup trucks actually wore their seatbelts. The question is, at a 10% significance level, can we reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and trucks? So the sample supports that the percentage is the same. The question is, is this sampling comparison indicative of the actual population? And it's our job to find out. So we're going to start, again, we're looking at the step-by-step procedure. We're going to start at the beginning and verify some hypotheses. We're going to verify the samples are random and independent, and then we're going to have to figure out what our x1, x2 are to compute our p bar, q bar, and then we're going to have to build out what these values are and verify that they're all greater than or equal to 5. So let's take a look. So let's see. Step 1, we're going to write, note, the samples are indeed both random and independent. There's a couple ways to see that. I mean, the randomness is clearly just given in the problem statement. The independence can be gleaned, for example, from the fact that the sample sizes are different, or by just interpreting sort of the circumstances of the problem. What we need now is we need access to x1 and x2. What is x1 and x2? Well, remember that, and we'll write this maybe parenthetically, right? X1 was equal to the sample size for the first sample multiplied by the population point estimate, p hat, where p hat here is exactly the sort of percentage that we're trying to identify within this sample. So this equation allows us to, if given 2 of them, solve for the unknown. In this case, for example, we're given the sample size of the cars, and we're told what percentage of them wear their seatbelts. So we're given the N1 and the P1 hat. We can take their product to figure out my X1. If you want to organize this in some sort of organized fashion, I suppose you could build a tiny table out of it. We could put like cars here. We could observe that N1 is 150. The P1 hat is 0.86. It's the decimal representation of 86%. And so their product, X1, is of course equal to 129 if we compute it. We can do the same thing for trucks. Here the sample size was a little bit bigger, it was 200. The percentage of people in the sample who wore their seatbelt, which we're going to call P2 hat, was a little lower, that was 74%. And so if we take their product, we're getting X2, which is equal to 148. And so now that we have this information, we can use this and put it into the formula for P hat, which is right here. It's the sum of the x's over the sum of the n's. So we're going to put that here. We're going to find that P hat is equal to x1 plus x2 over n1 plus n2, which is going to give me 129 plus 148 divided by 150 plus 200. That'll give, the numerator is 277, the denominator is 350, for which their quotient is approximately 0.7914. So this is my weighted estimate, P hat, and therefore Q hat, which is of course 1 minus P hat, is going to be equal to 0.2086. So we have verified some of our original hypotheses. We have found our weighted estimates, P hat and or P bar and Q bar. We've verified that the samples are random and independent. Going back to our list, the next step is to verify that these 4 products are all at least 5. Well, let's compute them. We're going to write since, and now we're going to compute all of our products. We'll have N1 P bar. If we write that out, that's 150 times 0.7914. That computation will yield 118.71. Indeed, that's greater than 5. We'll compute N1 Q bar, which is 150 times 0.2086. That'll give 31.29. That's greater than or equal to 5. So that's 2 of the products we need to verify. Now let's check the second sample. That's N2 P bar, which is 250 times 0.7914. Not 250, 200. That product will give 158.28, greater than or equal to 5. And lastly, N2 Q bar is 200 times 0.2086, which will give 41.72, which is, of course, greater than or equal to 5. So now that all of our hypotheses have been verified, we observe that since this occurs, we can now use a z-test. Not just a z-test, right? Technically, it's a 2-sample z-test. A 2-sample z-test. So all of that was just to verify our hypotheses. Now we know we can use this hypothesis test, so let's actually do it. Step 1 of the hypothesis test, of course, is let's see what the claim is. What is the claim? Well, they literally tell us, can you reject the claim that? So everything that follows the words claim that. What is it that they're claiming? The claim that the proportion of occupants who wear seatbelts is the same for cars as they are for trucks. That's the claim. So the claim is the 2 proportions are equal. That's the claim. Well, remember that equality is always an attribute of the null hypothesis. So in this case, it seems that our null hypothesis is that the 2 proportions of the populations are equal. And the alternate hypothesis is, of course, the opposite of that they differ, they're unequal. And it would seem that the claim lies at the feet of the null hypothesis. Now, depending on the nature of the test, which is indicated by the symbol living inside the alternate hypothesis, we need to find our critical values. So let's find out. Let's say, since the alternate hypothesis is P1 not equal to P2, and just like before, we recognize the not equal to symbol. This is a 2-tailed test, parenthetically, with the level of significance 0.10. So that tells us sort of what area to work with. And remember, when you're working with the z-test, generally speaking, it is useful to draw a picture in order to argue what your rejection regions should look like. So in this case, probably the picture I'm drawing is, again, a normal curve like this. Here's a 0. Since it's 2-tailed, we know we have a negative z sub 0 and a positive z sub 0. And in particular, the 2-tailed test tells us that the sum of the areas for each of the tails here is equal to alpha. In particular, the area of one tail is equal to 1/2 alpha, which in this case is 0.05. So what we need to do now is go to our standard normal table, find an area of 0.05, and that'll give us our negative critical value. So let's go to our standard normal table at the end here. We're looking for 0.05. 0.05 is right here. So 0.05 is living halfway between those two critical values. And so it's halfway between negative 1.64 and 1.65. Halfway between those lives a critical value of negative 1.645. So that means our leftmost critical value is negative 1.645. So let's import that value. Here we just found that our negative one was negative 1.645, and our positive one is therefore positive 1.645. So what that means is that the rejection regions are any z values less than the negative one, 1.645 negative, and any z values that are greater than the positive one, 1.645. Our objective now, of course, is to find our standardized test statistic, see whether it lies within the rejection regions or not, and then determine whether we can or cannot reject the null hypothesis as a result. What is the standardized test statistic? Let's pop back up into our rule here. Our standardized test statistic is this formula. We've already found the P1 and P2 hats. We know what P bar and Q bar are, so it's simply a matter of writing down this formula and computing the results. So the standardized test statistic is, well, the formula is P1 hat minus P2 hat, that's the hypothesized difference in the population proportions, minus the hypothetical one, P1 minus P2, all over the square root of the weighted estimates, P bar Q bar, times 1 over N1 plus 1 over N2. Where if we plug in all the data we have, we know at the top we get 0.86 for P1 hat, 0.74 for P2 hat, minus 0, because again, P1 minus P2 in the case of a hypothesis test is always assumed 0, because that's literally what we're trying to break. And we're dividing that by, let's see, P bar, if we scroll back up here, we had P bar and Q bar were computed in the very first line. So let's import those numbers. We're going to get 0.7914 times 0.2086, that's P bar Q bar, times 1 over 150 plus 1 over 200. The denominator is square rooted. And if you go through and carefully sort of plug this into a calculator, you should be getting approximately 2.73, where this standardized test statistic clearly lives about right there. That's 2.73. Clearly, it's larger than 1.645, and so yes, this does live inside the rejection region. So if we write that down, we'll say that since 2.73 is indeed larger than 1.645, we elect to reject the null hypothesis. But what does that mean in the context of the situation at hand? The claim turned out to be the null hypothesis. So it turns out that with a 10% level of significance, there is enough evidence to reject this claim. So let's write that down. So we're going to say that, so there is enough evidence at the 10% level of significance to reject the claim. That, and what is the claim? We of course interpret it. The claim was that the proportion of occupants who wear seatbelts is the same for cars and trucks. So, based on the sampling data that was given, with 10% confidence, we've been able to reject the claim. So, of course, what does that mean? That means that our sampling difference, the fact that we had such a difference in seatbelt representation in our sample, is somewhat indicative of what's happening for the greater populations. So this is one example of conducting a hypothesis test for the difference between two population proportions. We're going to cover one last example. It's going to be very similar to the one we just did. So all the moves will be very similar. It'll mainly give us an opportunity to work through the content another time in order to sort of solidify the key differences that pop up when conducting a hypothesis test on proportions.